Think about the last time an app crashed on your phone while you were, like, in the middle of buying concert tickets or transferring money.
Oh, yeah, just staring at the loading spinner.
Exactly. You probably just stared at it and blamed the app, right?
Right.
But beneath that frozen screen, there is a silent, completely invisible dialogue happening.
A massively complex dialogue.
Right. Involving dozens of architectural layers, physical wires, and complex network handshakes that just, catastrophically failed.
And that's exactly what we're looking at today, the blueprint of that invisible world.
Yes, because today's source material has this incredibly powerful quote that I just love. It says, "Code is a consequence. Decision is the foundation. Welcome to the deep dive."
It's a great quote.
I really want you, the listener, to let that phrase sink in for a second, because it is incredibly easy when we're building software to get completely lost in the syntax.
Oh, absolutely. The specific functions, the trendy libraries.
The exact lines of code glowing on the screen, right?
Yeah, we obsess over the color of the bricks and just completely ignore the structural integrity of the blueprint.
Which is dangerous.
Extremely. A truly consistent, reliable backend isn't born from just, stringing a few endpoints together or picking whatever web framework is popular this week on social media.
Right. It emerges from a deep foundational understanding of network protocols.
Layered security, well-defined contracts, all of that.
And that is exactly our mission for this deep dive. We are stepping away from the syntax to build a robust mental model of backend architecture.
Getting back to the basics.
Exactly. We're going to explore the underlying theory that powers the entire modern web, starting from the deepest physical network protocols all the way up to complex API design.
And our guide for this is an exhaustive architectural text by Jefferson Otoni Lima, who's also known in the software community as Jeffotoni.
Right, and his perspective is just incredibly valuable for an exercise like this.
Yeah, he brings over 22 years of experience building high-performance distributed systems.
Yeah.
I mean, he's a senior software engineer, creator of the Quick framework.
And what really stands out in his material is his underlying philosophy, I think. He looks at the backend as a living, cohesive ecosystem.
Not just a disorganized collection of server routes.
Right, exactly. And he insists that before we even touch on how this architecture is implemented in a modern language.
Like Go, which we'll get into later.
Yeah, like the Go programming language. Before we get there, we absolutely have to master the fundamental physics of web communication.
Because to understand how data behaves, you first have to look at the literal roads the data travels on.
The actual physical wires.
Yeah. We have to start at the bottom of the network stack and trace the evolution of HTTP itself. Because it's easy to take the lightning-fast web for granted today.
Oh, we all do.
But the rapid evolution of HTTP is staggering when you look at the mechanics. We started back in 1991 with HTTP 0.9.
Which was incredibly basic, right?
Oh, completely. At that time, it was just simple GD requests. No headers, no metadata, no status codes.
Wow.
You literally just asked a server for a text document. The server sent you the document, and then the server immediately closed the connection.
So just a completely transactional, one-and-done interaction.
Exactly, which, sounds fine for a plain text page.
But imagine doing that today. Like, if you load a modern web page with 100 images, you'd be forcing the server to open and close 100 separate connections.
Yeah.
That sounds like a massive bottleneck.
It was a massive bottleneck. Every time you open a connection, the underlying transport layer has to do this complex setup.
Right.
That's why, by 1997, HTTP 1.1 completely changed the game by introducing the Keep Alive standard as the default.
Okay, so what does Keep Alive actually do?
So now, the server and the client could negotiate to keep a single connection open. They pass multiple requests through that exact same tunnel.
Saving all those computational resources.
Exactly. And today, the industry is moving into HTTP 3, which is an even more radical shift.
Oh, yeah.
Well, it moves away from the TCP protocol entirely. It uses UDP instead.
Wait, hold on.
Yeah.
I want to pause you right there, because I've always been taught that TCP is like the gold standard because it guarantees delivery.
Right, the reliable protocol.
Yeah, it makes sure no data is lost. Meanwhile, UDP is always described as unreliable. Like, it just fires packets into the void and hopes they arrive.
That is the traditional view of UDP, yeah.
So why on earth would the modern web move to an unreliable protocol?
Well, because that view misses the brilliant mechanism of HTTP 3. You are right that TCP guarantees delivery, but it does so through a very slow three-way handshake.
Okay, what does that look like?
The client says, hello, can we talk? The server replies, yes, I hear you, can we talk? The client says, yes, here is my data.
So there's a lot of back and forth before anything even happens.
Exactly, and that takes time. Plus, TCP suffers from something called head-of-line blocking.
Head-of-line blocking.
Yeah, so if you are sending 10 packets of data and packet number 2 gets lost in transit, TCP halts the entire line. Packets 3 through 10 just sit there waiting while the system scrambles to retransmit packet 2.
Which explains why my app might suddenly freeze, even if I have like 4 bars of cell service.
Precisely. It's waiting for that one lost packet. So what HTTP 3 does with the QUIC protocol...
QUIC, right?
Yes, QUIC. It bypasses that slow TCP handshake by using the lightweight UDP protocol as a base.
But doesn't that leave it unreliable?
No, because QUIC builds its own highly efficient reliability and encryption layer right on top of UDP.
Ah, I see.
It manages the lost packets independently without stopping the rest of the data stream. It's basically a faster, smarter traffic cop.
Okay, that clarifies so much. And, the text uses a brilliant educational analogy for this whole TCP/IP 4-layer model that really clicked for me.
The post office analogy.
Yes, I want to share it with you, the listener, to kind of ground this. So imagine you were sending a physical letter.
Okay.
The top layer, the application layer, that's you actually writing the letter on a piece of paper. This is where HTTP lives. Then you move down to the transport layer. This is where you put the letter in an envelope. This is TCP or UDP. It's the layer managing the delivery mechanism.
Makes sense.
Beneath that is the internet or network layer. This is the routing department, figuring out the best geographic path for your envelope to take.
Like which highways to use.
Exactly. And finally, at the very bottom, you have the data link and physical layer. This is the local post office and the literal physical truck driving your envelope on the asphalt road.
It's a great analogy. Because what's fascinating here is that a modern backend developer writing an API endpoint is sitting at the very, very top of this stack.
Just holding the pen at the application layer.
Right. But they are entirely dependent on the physics happening below them. That HTTP 1.1 keep alive feature we just talked about.
Yeah.
That isn't just a line of code. It's an active, deliberate dialogue between the server and the client at the transport layer to hold that physical truck at the loading dock so you can throw more envelopes into it.
I love that.
If you don't understand that underlying mechanism, you simply cannot optimize the system for millions of users.
So, okay, the physical truck has arrived at the server, the envelope is opened, and the HTTP letter is sitting there.
Safely delivered.
But a sealed envelope is useless if the data inside is just a random jumble of text. How does the server know if this data is asking for a web page, submitting a password, or trying to delete a user profile?
Because the network layer doesn't care about meaning.
Right. To get meaning, the client and server need an architectural style to govern their conversation.
And that introduces REST.
Representational state transfer.
Exactly. But Jeffotoni's guide makes a crucial distinction here. There's a vast difference between REST as a purely theoretical architectural style.
Like in a textbook.
Right. And a RESTful API, which is a backend that actually applies those theoretical constraints consistently in the real world.
But I think the absolute most important of those constraints is what he calls the uniform interface.
Absolutely. The core mechanism of a uniform interface is that a client manipulates resources through representations.
What does that mean in practice?
It means you, sitting on your phone, are not reaching directly into the server's memory and changing a row in its SQL database.
That would be a security nightmare anyway.
Totally. Instead, the client sends a representation, usually a structured JSON text file.
Okay.
And that file essentially says, here is what I want this user profile to look like now. The server reads that representation, validates it, and updates its own internal state accordingly.
So when we talk about how well an API actually implements this REST theory, the source material brings up Leonard Richardson's maturity model for APIs.
Yeah, the grading rubric.
Right. It's essentially a grading rubric for how RESTful a backend actually is, scaling from level 0 up to level 3.
Let's unpack those.
Yeah. So level 0 is what he calls the swamp of POX, which stands for plain old XML.
Great name.
It is. This is basically where you ignore the rules of the web entirely and just use HTTP as a dumb transport tunnel for remote procedure calls, or RPC.
To visualize an RPC, think of treating the server like a remote calculator. You aren't asking for a resource, You're just sending a command to a single chaotic endpoint.
Like pushing a button.
Right. You send a payload that says run the create user function, and then you send another payload to the exact same URL that says run the delete invoice function.
There is no structure at all.
None.
Which is why we move up to level 1, where you actually start organizing things by distinct resource URLs. One specific URL for users, a totally different URL for invoices.
Much better.
Then we hit level 2, which is where you start using the correct HTTP verbs. You get a user to read it, you post to create one, you delete to remove it.
And you start returning the correct status codes.
Right. But I have to push back on level 3 of this maturity model.
Oh, the controversial one.
Yeah. The text brings it up as the ultimate goal, but honestly, looking at how the industry operates, it feels like a total pipe dream.
You're referring to HTOS.
Yes. HATEOAS. Hypermedia as the engine of application state.
It's a mouthful.
It is. The underlying mechanism here is that the API should dynamically guide the client, right?
Exactly.
So if I make a request to look at a bank account balance, the API doesn't just send the balance back. It also sends a list of hypermedia links telling my app the next valid actions I can take.
Like a link to deposit money or a link to close the account.
Right. It acts like a website navigation menu, but for machines. But the text itself notes that almost nobody actually uses this in production.
That's true.
So why do we praise a theoretical model that mobile and web developers actively avoid?
Well, it represents a really fascinating tension between brilliant theory and operational reality.
How so?
Theoretically, HTOS is beautiful because it decouples the front end from the back end.
Okay.
The back-end developers can completely change the structure of their URLs or their workflows without breaking the mobile app. Because the mobile app isn't hard-coding anything.
It's just blindly following the links provided in the server's response.
Exactly.
But the reality is, human developers hate blindly following links.
Precisely. In practice, development teams prioritize rigid predictability. A front-end developer building a mobile app wants to look at an open API document.
Often called a Swagger doc, right?
Right. This is essentially a rigid, human-readable menu that says, if I hit this exact URL with this exact payload, I am guaranteed to get this exact response.
They want fixed contracts so they can generate static code and test it reliably.
Exactly. Setting up API gateways, managing versioning, generating client SDKs.
All these standard practices.
Yeah, all of them rely on fixed contracts.
Yeah.
So HTOS is this elegant theory that routinely loses to the practical need for hard-coded predictability.
That makes a lot of sense. So if level 2, using the correct verbs and statuses, is the actual sweet spot where the entire industry operates, then we need to make sure we are speaking that specific language perfectly.
We need to understand the strict grammar of the web.
Exactly. And that grammar has evolved significantly, right? Jeffotoni's guide contrasts Rust with other architectures to illustrate why this matters.
Yeah, you have SA from back in 1998, which was incredibly rigid, heavy, and relied entirely on complex XML parsing.
I remember SOP, not fondly.
No one does.
Yeah.
Then you have WebSockets, which create a two-way persistent phone call between the client and server.
Which is perfect for real-time things like multiplayer games or chat applications.
Exactly. And then you have server sent events, or SSE, which is an HTTP standard from 2006.
And SSE is suddenly incredibly relevant again.
Oh, hugely.
It differs from WebSockets because it's a one-way street. It's like a radio broadcast where the server talks and the client just listens.
Right.
So every time you watch a large language model stream an answer to your screen, generating text one single word at a time, you are almost always watching server sent events in action.
It's everywhere now. But regardless of whether you are building a standard REST API or streaming AI data through SSE, the grammar of your HTTP verbs and status codes remains vital.
Because the entire point of these codes is to give the client immediate, predictable context about what just happened.
Exactly. Let's drill into status codes for a second, because I feel like everyone knows 404 means not found.
And 500 means the server completely crashed.
Right. But the source points out some really specific, crucial distinctions that elevate an API from amateur to professional.
What's a good example of that?
A great example is the distinction between returning a 400 bad request and a 422 unprocessable entity.
Oh, these are often confused by developers.
Absolutely.
I feel like I see 400 bad requests all the time when I mess up an integration.
And it is frequently used incorrectly. A 400 bad request should specifically mean that the physical syntax of the payload you sent is completely malformed.
So the server's parser literally cannot read it.
Exactly.
Yeah.
You forgot a closing bracket in your JSON, or you send a plain text document instead of a JSON object.
The computer is saying, I do not understand what this file is.
Right. But consider a scenario where you send perfectly formatted, structurally flawless JSON, but you leave out a mandatory business field, like an email address.
Or you provide an age of like -5.
Exactly. The format is perfectly valid, but the business logic fails. That's where the grammar gets highly specific. The server isn't confused by your formatting. It is blocked by your business rules.
So that should trigger a 422 unprocessable entity.
Yes. The server's saying, I understood the document perfectly, but I cannot process the semantics of what you're asking me to do.
Wow, that's a subtle but huge difference.
It is. When a backend developer makes these precise semantic distinctions, it makes debugging for the front-end teams infinitely faster because they know exactly where to look for the error.
So what this means for you, the listener, is that every piece of data you send or receive has to be packaged in a specific vocabulary.
Which we call serialization formats.
Right. And the text makes it very clear that the architecture dictates the tool you use.
Always.
For public-facing APIs, where simplicity and human readability are paramount, the industry standard is JSON. It is text-based, ubiquitous, and any browser can read it.
However, if you are building high-performance internal microservices, for instance, 2 back-end servers deep inside a data center talking to each other hundreds of thousands of times a second, in that case, JSON becomes a massive liability.
Why is that?
Because JSON is just text. For a computer to understand JSON, it has to read it character by character.
Figure out where the strings end and the numbers begin.
Exactly. And then convert all of that text into machine memory. Doing that text, parsing thousands of times a second, becomes a literal CPU bottleneck.
So the architecture demands a completely different mechanism like protobuf.
Right, which is used alongside a high-speed framework called gRPC.
And protobuf bypasses the text parsing entirely because the data is serialized into a dense binary format.
It is completely unreadable to a human looking at a screen, but it is natively lightning fast for a machine to process.
So we have outlined a robust, incredibly detailed theory of the web here.
We covered a lot of ground.
We understand the physical networking, the REST constraints, the Richardson maturity model, and the precise grammar of HTTP.
But theory is fragile.
Right. If you try to build this intricate system using a programming language that fundamentally struggles to handle high network traffic.
Your pristine REST API will still crash under pressure.
Exactly. That's why Jefferson Otoni Lima specifically pairs this entire architectural theory with the Go programming language.
And the transition in the text from pure theory to the Go language implementation is very deliberate.
Yeah.
Go isn't just an arbitrary choice here.
Not at all. To understand why Go is the engine of choice for this architecture, you just have to look at its absolute dominance in the DevOps and cloud-native ecosystem.
Think about the infrastructure that physically runs the modern web.
Yeah.
Docker, Kubernetes, Terraform, Prometheus.
They are all fundamentally written in Go.
Every single one.
Yeah.
Go was designed at Google specifically to solve the exact problems of network servers and distributed systems operating at a massive scale.
And it compiles down to a single portable binary file.
That's a huge advantage.
You don't need to install a massive runtime environment or virtual machine on your production server. You just drop the single binary file onto the Linux box and run it.
But beyond the deployment simplicity, the real magic of Go is its native network performance.
Which is deeply tied to how it handles concurrency.
Yes.
I really want to unpack this concurrency concept because the text provides a great mental model. When we hear concurrency, we often think of parallelism, right?
Doing a bunch of different things at the exact same physical millisecond.
Exactly. But in Go, concurrency is actually about structuring work efficiently so the machine is never sitting idle.
It is a vital architectural distinction. Traditional programming languages often use operating system threads to handle multiple requests.
But OS threads are incredibly heavy, aren't they?
Yeah, switching between them takes a lot of memory.
To use an analogy, imagine a restaurant kitchen. In a traditional language using shared memory, you have 5 chefs all crowded around the exact same cutting board, fighting over the same knives.
That is shared memory.
And it leads to constant collisions, bottlenecks, and complex bugs where one thread overwrites the data of another.
It's chaotic. But Go uses these things called coroutines, which are incredibly lightweight.
You can run hundreds of thousands of them simultaneously.
Easily. And instead of fighting over a shared cutting board, Go uses channels.
So channels act like isolated conveyor belts between the coroutines.
Exactly. The chefs do their work in total isolation. Those are the coroutines.
And they safely pass the chopped vegetables down the conveyor belt to the next station.
The core philosophy of Go is, do not communicate by sharing memory. Instead, share memory by communicating.
That is so elegant. And if we tie that beautiful language design back to the HTTP theory we spent so much time discussing, you see why Go is so uniquely powerful for building APIs.
Absolutely. Go comes with a built-in standard library package called nethttp.
Right.
It is essentially a production-ready web server right out of the box.
Yeah.
But, and this is a massive warning from the author, the language will not save you from making bad architectural decisions.
You still have to drive the car.
Exactly. Decision is the foundation.
So what is an example of a bad design choice a developer could make using Go's built-in tools?
Well, the source material gives a very stark warning regarding the router.
The router is the piece of code that looks at an incoming URL and directs it to the correct function, right?
Yes, Go provides a default global router for convenience, called default.ServeMux.
Okay.
The text explicitly warns to never, ever use this in a production environment.
Wait, if it's the default provided by the language, why is it so dangerous?
Because it is a global variable. Any third-party package you import into your project, say a helpful logging library or a performance profiler, it can silently register its own routes onto that default ServeMux without you ever knowing.
Oh, wow. So by just importing a helpful third-party library, I could accidentally give the public internet an invisible backdoor directly into my server's diagnostics.
Just because they share the same global router.
Precisely.
That's terrifying. You could deploy your application thinking you only have 3 endpoints, but you actually have 10. And 7 of them are exposing sensitive internal data.
Wow.
The architectural decision here is that you must intentionally design and instantiate your own isolated custom routers.
That makes total sense.
Furthermore, tying this all the way back to segment 1, you have to manually configure your server's hardware timeouts.
Right, because the language won't guess how long your connections should stay open.
Exactly. You must explicitly set a read timeout to prevent malicious clients from sending data at a trickle and permanently tying up your server's memory.
Like a slow Loris attack.
Exactly. You also have to set an idle timeout to manage those exact HTTP 1.1 keep alive connections we talked about earlier.
So the server has to know exactly when to cut a silent, inactive client loose to save computational resources.
Go gives you a Ferrari engine, but if you don't steer, you will crash.
Man, let's take a breath and look at the journey we've just been on. We started down at the literal physical wires, exploring the difference between the heavy guarantees of TCP and the lightweight speed of UDP and HTTP3.
We climbed up the stack to explore the theoretical constraints of REST and the uniform interface.
We defined the precise, predictable grammar of API status codes, knowing exactly why a 422 unprocessable entity is different from a 400 bad request.
And finally, we saw how a language like Go, with its isolated coroutines and strict network controls, is the perfect vessel to execute this massive theory in a production environment.
It really validates the author's core premise. A backend is not just code. It is a highly complex system built on a series of deliberate, interconnected choices across multiple layers of abstraction.
It really is.
So the next time you open an app on your phone, whether you are fetching a simple list of user profiles or watching a large language model stream text to your screen,
I want you to visualize what is actually happening.
visualize that invisible, rapid-fire handshake of network protocols. Visualize the deliberate architectural constraints of REST, keeping the massive flow of data organized.
Appreciate the robust, invisible decisions supporting every single tap on your screen.
But this leaves us with an incredibly provocative question, one that builds directly on the evolution we've mapped out today.
Yeah, we mentioned earlier that server-sent events are currently being used heavily for streaming responses from AI models.
Right.
Artificial intelligence is fundamentally changing how clients interact with servers.
Because the client is no longer always a human looking at a screen.
Exactly. Think back to the Richardson maturity model and level 3, Hadeways.
The one nobody uses.
Right. We established that the main reason HadeAS failed to catch on is that human developers wanted the rigid simplicity of hard-coded Swagger documents. Humans demand predictability.
True.
But as autonomous AI agents increasingly become the primary consumers of APIs, rather than human developers reading documentation, will that model shift?
Oh, wow. That is a fascinating thought because an AI agent doesn't need a human-readable open API document.
It doesn't. An AI agent is perfectly capable of parsing a server response, instantly reading the hypermedia links, and dynamically navigating an API on the fly to figure out the next steps to achieve a goal.
So will AI be the force that finally pushes the web to adopt level 3 HATOS?
Will we see a future where APIs no longer have rigid, fixed contracts at all, but instead act as dynamic, constantly shifting landscapes designed exclusively for machine agents to explore?
If that happens, it will fundamentally alter the base decisions that form our backend foundations.
It changes everything.
That is an incredible thought to leave on. The web is a living ecosystem, and it is never finished evolving. But no matter who or what is consuming the API, the fundamental truth of the architecture remains the same. Code is a consequence. Decision is the foundation. Thanks for joining us on this deep dive.